Dear friends, I am Dr. Keyur Parikh, cardiologist at SIMS Hospital, Care Institute Medical Science, Ahmedabad. This is continuation of our e-learning courses for physicians and doctors. Today we will be discussing TAVR or TAVI. What is TAVR or what is TAVI? TAVR is transcatheter aortic valve replacement. TAVI is the same thing, transcatheter aortic valve implantation, which is the new paradigm in interventional cardiology for treatment of aortic stenosis, which has been practiced for last decade but has become very popular in last few years, more so since US FDA approved the use of TAVI, transcatheter aortic valve implantation, for both severe aortic stenosis with high risk patients as well as now for intermediate risk patients. The procedure involves usage of catheter-based bioprosthetic aortic valve, which is delivered through different routes but mainly femoral artery, and is placed at the site of previous aortic valve, native aortic valve, without removing the native valve. So let's go ahead and discuss an interesting case of TAVI. This is a case where the patient was 85-year-old gentleman with very tortuous aorta, where first time in India we used a 3D printing model before doing the procedure and used the model to create a artificial anatomy using 3D printing and used that to do the procedure in that model, and subsequently we did this procedure live where it was done very smoothly within 30 to 45 minutes in the patient. We are now presenting a case of transcatheter aortic valve implantation, TAVI, after 3D printed model demonstration, first in India. The heart team at CIMS Hospital, SIMS Hospital, Ahmedabad, included myself, Keyur Parikh, as primary operator, with Dr. Milan Chugh, Vipul Kapoor, and the entire heart team at the hospital. Dr. Dhiren Shah and Dhaval Nayak and the anesthesia team of Dr. Niren Bhavsar, Hiren Dolakia, and Chintan Sheth are part of the cardiac anesthetists. I have no actual or potential conflict of interest in this presentation. This is an 84-year-old gentleman, very active lifestyle, psychologically normal, who had a history of coronary artery disease, triple vessel disease, who had a successful stage PCI to left circumflex artery, left anterior descending artery, and right coronary artery, 7th of February, as a prelude to the treatment of his aortic stenosis. He is also awaiting major spine surgery requiring general anesthesia. This is the surgery time showing 4 to 6 hours in the West building. The West, his clinical and echo presentation showed severe aortic stenosis, cardiovascular calcified aortic valve, grade 2 mitral regurgitation, and mild LV dysfunction. We will now show the 2D echocardiography, which shows moderately severe aortic stenosis with calcified aortic valve. This is another preoperative echocardiogram showing the calcific aortic stenosis. The color Doppler, 2D color Doppler, shows and confirms severe aortic stenosis. Non-invasive imaging measurements were done which showed the thick calcific aortic stenosis with aortic valve area of 0.50 centimeter square and a pressure gradient peak of 103 millimeter mercury and a mean gradient of 52 millimeter mercury. Mitral valve is calcified but open, and other valves were structurally normal. LV ejection fraction 60% with concentric LVH, and there is mild to moderate mitral regurgitation with mild PAH of 36 millimeter mercury. CT angiography was done before the procedure using TAVI protocol, and it was decided to use femoral access. Right femoral artery, common iliac artery, was 8.2 millimeter by 9.0 millimeter. External iliac artery was 6.8 millimeter by 7.6 millimeter, and common femoral artery was 7.4 by 7.5 millimeter on the right side. On the left side, common iliac artery was 7.8 by 9.6 millimeter. External iliac artery was 6.9 by 7.0 millimeter. And common femoral artery was 8.4 by 8.9 millimeter. So both femoral access were adequate, wide open, and minimal to no calcification. CT analysis of the aortic root and aortic valve showed aortic annulus diameter at 22.1 millimeter, sinus of Valsalva diameter at 32.7 millimeter, and sinotubular junction diameter at 25 millimeter. Again, the detailed analysis showed the perimeter of the annulus at 75.3 millimeter and derived perimeter was 24.0 millimeter. Sinus of Valsalva diameter varied from 30.4 at the left coronary cusp, 31.6 at right coronary cusp, and non-coronary cusp it showed 28.8. This showed fairly dilated or fairly sized sinus of Valsalva diameter. Sinotubular junction diameter was 20.5 by 26.9. Aortic valve calcification was mild to moderate, very appropriate for TAVI procedure. LVOT diameter again was 20.1 by 25.7, minimum and maximum diameter, and maximum ascending aorta diameter was 31.9. Sinus of Valsalva heights were also decent and good. At left coronary cusp 26.1, at right coronary cusp 24.4, and non-coronary cusp 24.4. Final CT analysis report showed very appropriate diameters at the annulus, sinus of Valsalva, sinotubular junction, and the left and the right coronary ostia heights were adequate at 21.5 millimeter for left coronary ostium and 19.8 for right coronary ostium. So what was the problem in this patient? Why did we think of 3D printing? The problem was that multi-slice CTA showed very double curved tortuous aortic arch with 66% aortic angle, more than the optimal angle. This does show the tortuous aortic arch. So the aortic root, which was double curved tortuous with a sharp aortic root angle of 66%, led to our belief that this will be a very difficult case of transcatheter aortic valve implantation. We then decided to use 3D printed model of aortic arch, ascending aorta and aortic valve to do a pre-procedure mock TAVI in the cath lab. So what's 3D printing model? 3D printing model or three-dimensional stereolithographic, which is .stl printing, can be used to convert clinical imaging data into life-size, patient-specific physical models replicating the anatomic characteristics of calcific aortic valve as well as replicating the anatomy of the aorta. These full-scale models require a combination of several technologies, including high spatial resolution ECG, CT angiography, computer-aided design software, and fused multi-material 3D printing. 3D printing is a breakthrough technology that offers improved patient care outcomes, trainee education and technical skills, and is very useful for patient and caregiver counseling. The steps in data processing for 3D printing includes the first step being CT imaging, three-dimensional in nature, followed by segmentation, followed by conversion of DICOM images and DICOM movie to the STL stereolithographic imaging, and finally printing of the 3D model. This shows 3D patient-specific model reconstruction from CTA data. This shows conversion of patient's CT image into blood volume reconstruction from CT data, finally reconstructed valve tissue and calcium as well as aorta from various plastic, semi-plastic or complex models, final 3D digital model of aortic arch with calcified valve, and the final 3D printed patient-specific model. The critical role of 3D modeling in TAVI again is to evaluate the aortic arch curvature, evaluate the landing zone, and to size the valve properly, customized to each patient in case of complicated valve anatomy, especially in bicuspid aortic valve, or in case of tortuous aorta, the aortic arch. So this is the case where you can see the complicated tortuous aortic arch in our 3D model and the 66% aortic root angle. In the middle image of the model of an otherwise normal patient, the normal aortic arch and the 40 degrees aortic root angle is much simpler anatomy compared to the left-sided image which shows highly tortuous aorta. That tortuous aorta can also be visualized in the last image on the far right, as the image of the 3D model is rotated in this movie. You can see the curvature again and the angulation. Since this was one of our first case involving such a tortuous aorta and aortic arch, we decided with this 3D printing and went ahead. Again the CT angiography image followed by center image showing customized 3D printed model, the aortic valve in the far right insert, and the on-table mock demonstration. Subsequently, we took this model to the cath lab and decided to do a mock TAVI in this model using fluoroscopy imaging and the delivery system of the Medtronic Evolute R. We first used a regular wire and we found very difficulty with the implant stiff wire, so we decided to use a Confida wire. With the Medtronic Confida wire, you can see we still had difficulty to advance the Evolute delivery system across the double tortuous aortic arch. No doubt this arch was semi-rigid, whereas the human aorta is more flexible, but in the 84-year-old patient, we felt that there will be some degree of rigidity. So we tried and we found that using a synchronized pulling of Confida wire and pushing of the Evolute delivery system helped us smoothly go across the aortic arch as seen on the right side in the fluoroscopy image. So lessons after mock trial on the 3D printed model was wire movement was important to give support to the delivery system. Secondary operator should be expert with synchronized wire movement, and we decided to keep the Lunderquist wire as a backup in case the confida did not work well. Decision to pre-dilate with balloon aortic valvuloplasty was made to facilitate the crossing of the aortic valve with the 66-degree aortic root angle. Evolute R 29mm was selected, which conferred in terms of the annular diameter, annulus parameter, sinus of Valsalva diameter, sinus of Valsalva height in relation to the patient's measurements. We also kept the Lunderquist wire in the center image, and we discussed Boston Safari wire, which is not available at our center, and we decided to use the Confida wire as the wire of first choice. We also made sure there was a proper view box in the cath lab with CT angiographic images available, which you can see here, the 3D images as well as the radiographic image. We decided to use ProGlide system. We went from the left femoral artery, as you can see. We put 2 ProGlides and then went ahead with the 18 French sheath and crossed the aortic valve using Terumo glide wire, followed by the wire exchange using Implants 1 catheter, followed by pigtail catheter, and finally the Confida wire insertion. Balloon aortic valvuloplasty was done by inserting the balloon through the valve and pre-dilated the valve with the balloon. 18mm balloon was used. Subsequently, 29mm Evolute R valve was inserted on a delivery system. And as you will see, we did find resistance and difficulty when we reached the aortic arch. At this time, the second operator started tightening the Confida wire with a taut filling, and we were able to slide the Evolute catheter system across the aortic arch in a reasonably synchronized movement between the primary operator and the person who held the wire. The Evolute R was easily crossed across the valve, and valve deployment was done by the secondary operator in the traditional way. Since Evolute R does have a recaptured option, we used that and we kept the position 3 to 4 mm below the aortic annulus. You can see the valve being deployed slowly. Once the valve was deployed, the system was pulled back. TE was also used for the positioning. Once the delivery system was removed, proper measurements were done across the aortic valve, showing total resolution of the gradient. An extra ProGlide was introduced, and finally the groin was closed with the ProGlide system. So you can see in a patient with tortuous aorta and 66-degree aortic root angle, the procedure was done very smoothly. This is the post-operative echo, and it shows resolution of the gradient and patent aortic valve, bioprosthetic TAVI valve. This is another image of post-operative echo. Final pre and post-operative Doppler gradient shows resolution of the gradient across the aortic valve. Take-home messages. So this is one of the first cases in India and otherwise to use a 3D printing model where we were able to evaluate in the diseased patient's case the diseased patient specific anatomy, and this helped train our assistant doctors as well as create a patient replica. We can use this even to look into the very minute details of the aortic valve and aortic stenosis. And we found that this was able to influence our acute procedural success. Lessons learned from 3D printing includes that appropriate case selection is key. Discussion of clinical priorities are very vital. Quality control is very important, of paramount importance. So active involvement of the cardiologist with expertise in cardiac imaging is essential during key steps of 3D modeling such as segmentation, design, printing. Close communication with the 3D engineer is very important. There are many different options for 3D models such as rigid, multicolor, single color, semi-rigid, flexible. We used a semi-rigid, semi-flexible model because that was only available to us. Eventually this model used will be determined by the needs of the clinical team, ideally for teams taking care of complex patients, and the cost in India varies between 10,000 rupees to 100,000 rupees. Our model cost around 15,000 rupees, which was very acceptable. Final conclusion that this provides 3D printing model provides cardiac specialists with intuitive perception of the cardiovascular anatomy and measurements in preparation of the TAVI, and may offer greater possibility of simulating patient-specific complex structure. We use this model from a company called Anatomize 3D Healthcare, the website being www.anatomize3d.com. I thank all of you that you have enjoyed this case. I am Dr. Keyur Parekh from SIMS Hospital, Cardiovascular Department. Thank you again.